Welcome to Chapter 13, Part 5. The title is Elvis. The first question I want to pose in this presentation is, who are dogs? The domestic dog is a subspecies of the gray wolf, a member of the Canida family of the mammalian order of Carnivora. The term domestic dog is generally used for both domesticated and feral varieties. The dog was the first domesticated animal and has been the most widely kept working, hunting, and pet animal in human history. So watch this video and think about this wolf chasing this calf. And the question to think about is whether or not the wolf is optimizing the path to the calf. In other words, obviously, the wolf is trying to catch the calf, but has the wolf developed an instinct and an ability to find the shortest path or the fastest, quickest path to the calf? So in a sense, the way to think about it is, if the dog slash wolf is going to catch the calf, then the distance traveled, the time it takes to cover that same distance, is going to have to be less for the dog than the calf. So the question is really that I want you to think about is whether or not this wolf has an instinct that allows it to find a faster path than the prey is following. And what is going through the mind of the wolf right now? I speculate that what is in the mind of the wolf is, kill the rabbit. And yes, the wolf catches the calf. It doesn't always go down that way, but that's how it went down in this case. So enter Elvis, the domestic wolf. And the gentleman with these 3 Welsh Corgis is a man named Professor Pennings. And I believe this black and tan color Welsh Corgi right here, I believe the coloring is black and tan. In any case, this is Elvis. I don't know the name of the other 2 Corgis. But anyway, Tim Pennings is an associate professor of mathematics at Hope College in Holland, Michigan. His research, done collaboratively with undergraduate students, is dynamical systems and modeling. Now, Professor Pennings and I have very similar backgrounds. I also have a graduate degree in dynamical systems and modeling. And so when I read this article that was published in Mathematics Teacher, I thought, man, what a great example, what a great modeling problem. And here's the basic idea. Hopefully you had time to read the whole article before the presentation, but if not, I'll explain briefly what the basic idea is. Professor Pennings likes to go and play fetch with his dog, and they go to Lake Michigan. And I'm sure many of you, and myself included, have spent time at the river or the lakes or even ocean playing ball or throwing balls and sticks for our dogs. And so Professor Pennings does this routinely. And so the idea here is that Professor Pennings is here with, here's the lake shore. And so Professor Pennings is here playing fetch with his dog Elvis, throwing the ball for his dog. And here, let's see, I'll draw a little sketch of Elvis. And I'm assuming Elvis is probably wagging his tail in anticipation. So Professor Pennings throws the ball out into the lake, and the ball splashes out here. And then he sends Elvis out after the ball, or Elvis takes off after the ball. So what Professor Pennings was noticing was that Elvis didn't just dive right into the lake, but Elvis would run a certain distance down the lake and then jump into the water and swim out to the ball. And Professor Pennings began to wonder, what's this behavior all about? Now, the dog could just jump straight into the water, right, in its excitement and just swim straight out to the ball, right? Or, in some ways, that would make sense, right? If the dog was not trying to optimize the path, it might just jump straight in the water and go straight out. Or the dog could run down the beach as far as possible. Well, one way to think about it is to minimize the swimming distance, right? So if the dog didn't like to swim, then maybe it would run as far as it could and then boom, jump into the water and swim. Or the theory that we're going to build up to is that the dog actually isn't thinking about what it likes or doesn't like about running or swimming. What it's saying is, I'm going to get to this ball as soon as I possibly can, because to me, the ball is the prey. And I used to train dogs. I spent about 10 years in doing competitive obedience training, and I learned a lot about dog behavior. And dogs have two basic drives. One's called defense drive, and the other's called prey drive. And dogs chase balls for the same reasons for the same reason you don't want to run from an animal like a mountain lion. Because when you run from a mountain lion, it triggers an instinct in that animal that the animal many times just can't even control. It will chase you. When you throw a ball for your dog, many dogs, they cannot control themselves. They see the ball as the rabbit, as the prey, and they are instinctually driven to chase that ball as hard and fast as they can. And it's also why you might also observe your dog when it does catch the ball, especially even if you're not using a ball, but you're using one of those balls with the string or something, or some other type of thing like a chew toy. Many times dogs will chase that toy, grab it, and then shake it. And when they're shaking that toy, they're killing the prey. Anyhow, I think it's a very interesting kind of a mathematical problem to talk about. And so the question again is whether or not Elvis is, here's the question: is Elvis optimizing the path? Or another way to say that is Elvis minimizing the path, the time it takes to get to the ball. Okay. Now we're going to make a couple of simplifying assumptions, or a few as we go along here. So we're going to assume the dog is running. Oops, how do you spell dog? D-O-G. We're going to assume the dog is running and swimming at top speed. In other words, the dog is in prey drive. So the dog is running as hard as it can. And what that does is it makes the running and swimming times, I'm going to call R well, I'll do that later, but we're going to assume that those speeds are constant. And that makes the problem a little bit easier, because by assuming the speeds are constant, then we can use the familiar distance equal rate times time formula, which gives us the distance traveled when an object's moving at a constant rate, and the distance is equal to the constant rate times the time spent traveling. Of course, we're actually interested in time here, so what we're going to do is solve this equation for t by dividing both sides by r, and we'll find that the basic relationship between the rate and the distance is d over r, and that's equal to the time spent traveling, or the time it took to run that distance or swim that distance. Now, there are two distances in question here, or that apply here. The first is, and first of all, let me describe this diagram here. So A is where Professor Pennings and Elvis start. So Professor Pennings throws the ball from A to B, and B is where the ball lands. So the distance from A to D is the distance the dog chooses to run down the beach, and then the distance from D to B is the distance the dog chooses to swim. Now the distance from A to C is, I'm going to think of that as the maximum distance the dog would choose to run down the beach, which would also minimize the swimming distance. So really, there's kind of a couple of extremes here. Well, there's a third extreme that we're not going to consider. The third extreme is, and of course this is the right angle point. This is the perpendicular point from the shoreline to the ball, which would create the shortest swimming distance. There's also an option that the dog overshoots this point C, runs too far down the beach, and then jumps in and swims, but that's obviously not going to be an optimal path. So we'll rule that out and we'll focus on the most likely optimal path. Now let me talk about this a little bit more. Dogs swim much more slowly than they run. And so it's unlikely that the path that involves all swimming is the fastest path. It's also unlikely that the path the dog runs that maximizes the running distance down the beach and minimizes the swimming distance, the path from A to C to B, is probably not the fastest path to the ball either. Likely the fastest path is the path where the dog chooses to jump into the lake at some point D, partway to C, and then swims a certain distance. So that's the theory that we're working on, is this is what the dog's actually doing. And that means we have two distances. We have D1 here and we have D2. And then we have two rates, and we're going to call R, and I'm following the same notation in the article, R is the top speed running. So this is Elvis's top speed, which is a rate, of course, running. And we're going to call S Elvis's top speed swimming. And again, we're going to assume that that R and S are constant because the dog's at top speed. Well, what that means then is this particular equation for the Elvis problem, the time equation, has two parts. That would be D1, the distance the dog chose to run down the beach, divided by R, which is the dog's top speed running, plus D2, which is the distance the dog chose to swim, over S. Now the notation in the article is a little bit different. So I'm going to switch, and there's a reason for that as well, because we're going to do some other mathematics here. And so I need to do a couple of things. First of all, we're going to use function notation to be consistent with the notation in the book. So t here, I'm going to call t of y. So that's time as a function of y. And the whole problem is keyed off the independent variable y, which is the distance the dog chose not to run. That's how I like to think about this. Okay. Now, and the reason for choosing this variable as the independent variable it's a simplifying organization of the equation, because really we're going to do this in a single variable case. So the idea here is I want to focus on one single variable, and that variable is going to be y. Okay, so let's talk about D1. Well, if we introduce another variable here, and we're gonna introduce a variable z, which is the distance all the way from A to C. Okay, that's going to be z. Now, given that, now that we've defined the distance from A to C as z, we can rewrite D1 in terms of y as z minus y. In other words, the distance AD, D1, what I called D1 originally, is equal to the distance from A to C minus y. So D1 over R can be written as z minus y divided by R. And now let's talk about distance 2. Well, DBC, triangle DBC, is a right triangle. Therefore, D2 can be found using the Pythagorean theorem. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And if we do the algebra here, we'll find that D2 is equal to the square root of x squared plus y squared, and then that's divided by s. This is the equation that Professor Pennings has in his article. Now, I want to do a little bit of calculus. And some people, myself included, believe calculus is the most important intellectual discovery in the history of the human mind. That's sort of a bold statement. If you've never had calculus, then I strongly encourage you to take calculus just for your own growth, even if it's not required for your major. But that's just my pitch for calculus. Now, let me show you what we can do with calculus. So this problem is, and again, if you're not interested in the calculus, it's certainly not a requirement for this course. Feel free to skip ahead through this part of the presentation on the calculus. So one field, one branch, or one application of calculus is something we call optimization. I'm going to switch my pen color to white. And the idea with optimization we can use calculus to maximize and minimize functions, or to find the maximum and minimum of functions. So the function that we have here is a time function. Time is a function of y. And the equation that we derived was z minus y divided by r plus the square root of x squared plus y squared divided by s. Now, there's a process in calculus whereby we take something called the first derivative, set it equal to 0, then solve for the independent variable, or solve for y in this case. Okay? And so that's what I'm going to do here. And again, this is the calculus part, but like I said, I want to show, for those of you that have had calculus or have an interest in calculus, I want to show you how this works, so, and where the equation came from. So what I'm going to do is take what's called the first derivative, and there are formulas for doing this. The first derivative of this first term is negative. The derivative of z is a constant here in this particular equation. Now I know everything's constant except y, because t is a function of y, and that means I'm going to hold all the other unknowns in this equation constant. So the derivative of z is 0. The derivative of y is 1. And so I have negative 1 divided by r. And the second equation right here, the second term in the equation, I'm going to pull the 1 over s out in front because it's a constant. And then I'm going to start with with the square root function. The derivative of the square root is 1 over 2 times the square root. And so I still have the radicand here, x squared plus y squared. And then the chain rule tells me that I should also take the derivative of the inner function y squared, which is derivative of y squared is 2y. So the 2's are going to cancel there. And so this, let's see, so t prime is equal to negative 1 over r plus 1 over s times y divided by square root x squared plus y squared. Now, what we need to do is set this first derivative, t prime of y, equal to 0. And what that means is negative 1 over r, which is plus 1 over s, times y divided by the square root of x squared plus y squared, which is t prime of y, is going to be equal to 0. So add 1 over r to both sides. That gives us, this is all algebra now, 1 over s times y over the square root of x squared plus y squared is equal to positive 1 over r. Now I'm going to get everything in the numerator. I'm going to multiply both sides by r. So I'll have r times y here on the left side of the equation. And I'm going to also multiply both sides by s and square root x squared plus y squared. Now, I need to solve this equation for y, so I'm going to square both sides. And let's see, let me rewrite what we had there. So we had ry squared equals s square root x squared plus y squared squared. And that gives us r squared y squared equals s squared times x squared plus y squared. So we just eliminated that radical. Things are looking good here. I got a y squared here on the left. I got a y squared locked up in the parentheses here, so I need to get that y squared out of the parentheses. I need to distribute s squared to both sides. So we have s squared x squared plus s squared y squared. Subtract s squared y squared from both sides. So we have r squared y squared minus, oops, it's supposed to be a minus, s squared y squared equals s squared x squared. So we'll factor out the common factor y squared. We have r squared minus s squared times y squared, and that's equal to s squared x squared. Divide both sides by, both sides of the equation we'll divide by r squared minus s squared. And we have y squared equals s squared x squared over r squared minus s squared. Almost there. I need to take the square root of both sides. So y is equal to plus or minus the square root of s squared x squared divided by, that's supposed to be a square, r squared minus s squared. Now, okay, y, we're talking about distances here, so distances are never negative, so I'm going to just cast away the negative or disregard the negative square root. So you might come up here. So what we have here is y equal the square root of s squared plus x, or times x squared, divided by r squared minus s squared. So now Professor Pennings wrote this in a particular way. I'm going to go ahead and show you the algebra steps to get what Professor Pennings got, but really the most important thing for the purposes of the video that I'm going to show you, or the demonstration I'm going to give, is that this whole thing is equal to, we can rewrite this whole thing as the square root of s squared over r squared minus s squared, okay, times that radical ends there now, times x, because the square root of x squared is x. Now, and again, x is going to be assumed to be a positive value, so I'm not going to worry about the absolute value. Okay, now, and of course this is the principal square root anyway, so I wouldn't need it. But in any case, or actually I would need it because it is the principal square root, but I don't want to get into all that because x is going to be assumed. If you look back at the diagram, x is the distance out from the shoreline out to the ball, so it is a positive quantity in reality. Now, the main thing to see here is we have a constant times a variable x equal to another variable y. This is a linear form. So basically what this is showing is that if Elvis is optimizing the path to the ball, then the relationship between y and x is a linear relationship. That's where statistics can come in. Now, just for the heck of it, I'm going to go ahead and show you the algebra that Professor Pennings used to get his particular form. And he was using that form of the equation for a different purpose. But in any case, let's see. So if I start with this form right here, let's see, I can divide the radical into two pieces, x squared in the numerator times s. Now I'm going to throw the s squared down in the denominator at the same time, okay? And this looks a little complex, but basically, algebraically, s squared in the numerator is the same as 1 over s squared in the denominator. And then that's going to be times r squared minus s squared. So now the numerator becomes x, and the denominator becomes the square root, okay, of 1 over s squared. Now, r squared minus s squared is the difference of two squares. So that can be factored into r plus s times r minus s. And if you, oops, I need a square on my s right there, okay? 1 over s squared times that. Now, if I split 1 over s squared into two parts, okay, one of which is going to go with the r plus s, the other 1 over s is going to go with the r minus s. Lo and behold, what you find is that x, this simplifies to x over the square root. And I'm distributing the 1 over s into this parenthesis first. So we have r over s plus s over s, which is 1. And we have, again, distributing this 1 over s. We have r over s minus s over s, which is 1. So that's the form that Professor Pennings has in his article. And again, like I said, this is the main idea here is that if the dog is optimizing the path by minimizing time, then the relationship between x and y should be a linear relationship. So let's look at this from a statistical point of view. And again, this is really a common question in statistics that is a good place to start, which is, what's the theory here? Well, the theory has multiple parts, okay? And they all kind of boil down to this one idea of these two variables being related linearly. So that the theory starts with Elvis is chasing the ball, and the path Elvis is following is the minimum time path to the ball. We do some calculus, and we find that the minimum time distance under our assumptions would result in an equation between, or a relationship between x and y, where we have 1 over the square root of r over s plus 1 times the square root of r over s minus 1 times x. And again, this is a linear form because this quantity, this complicated looking, since r and s are constants, this complicated looking quantity right here, this is constant. So what we can do is we can say, and this is a theoretical constant about the population of all x and y's. So we can call that whole thing beta, and we can say that our theory is that the relationship between y and x is y equal beta times x. So then what ends up happening is we focus on the slope. This is starting to sound familiar. So the theory is, okay, let me write this out. So the theory here now in terms of math is that beta, the true slope for this linear relationship, is not 0. This means the dog is actually optimizing the path. So if I look at it again in terms of a statistical hypothesis with the null and the alternate, The null assumption is that dog's just playing. Dog's just fooling around. Alternate is a little more serious, perhaps. Elvis the wolf is in full prey drive. In other words, this dog is trying to kill a rabbit. Anyway, now here we are now. We have a wonderful statistical hypothesis to test. This is how we do mathematics, applied mathematics. This is how we do statistics. We start with this idea. Is Elvis optimizing the path? We define variables. We make simplifying assumptions. The dog's running at a constant speed, flat out, fast as it can. And then we collect data and we test our hypothesis. So what Professor Pinnings did, again, if you read the article that I sent out as an announcement before this lecture, you would have read that, you know, that Professor Pinnings actually collected data on both X and Y's. And so first step in the analysis would be to draw a scatter plot. So here's a scatter plot of the XY data. Now, one of the really interesting things to me, well, one of the reasons to look at the scatter plot is because the previous theory I put down in the alternate was that beta was not equal to 0. Because I didn't necessarily have an idea. And I probably could have looked at that diagram maybe and thought about the fact that X and Y should be linear. I'm sorry, that the slope or beta should be a positive value because of the relationship between X and Y's. But I'm also seeing it right away in the scatter plot. So if there's a significant linear relationship here, it's going to be a positive relationship. And what that allows me to do is modify my assumption here, or my theory, okay? And let's see, I need to change the pen color. Okay, so my modified theory, or my refined theory now, again, the null is still that beta is equal to 0. And now based on this scatter plot, I can modify my alternate and say beta is greater than 0, okay? Now, the trade-off here, the motivation from going to not equal to a greater than is because by saying I understand more about the relationship, in other words, specifically that the relationship is a positive linear relationship, it's going to make my p-value even smaller than it would have been. The two-tail or not equal to two case always ends up with a larger p-value. In fact, generally in the two-tail or the not equal to case, the p-value is twice as big. Okay, so let's look at the calculator. Now, I've already entered this data, and if you haven't entered the data, just pause for a moment and go ahead and enter the data if you want to follow along. Okay, so I have entered the data. I'm going stat edit to the editor. I created two lists, one called X, one called Y, and I've entered the data values into those lists. Now, we've already looked at the scatter plot. And again, we could draw a scatter plot again on the calculator, but I'm not going to do that this time. If I wanted to draw the scatter plot, or if you'd like to, you do 3 steps. Enter the data. It's already done on my calculator. Then configure stat plot and then do a zoom 9. Okay, but anyway, we've already looked at that. So I'm going to go to stat, and I'm just going to jump right into the linear regression t-test. So I'm going to go to tests, and I'm going to go to linreg t-test. And what we need to do is put Y for the X list, Y for the X list, X for the X list, list X, and then list Y for the Y list. And the correct alternate assumption is beta is greater than 0. Now, I'm not even actually interested in the best fit line in this case. One of the things that's really interesting about this particular problem is what we're looking for is whether or not the relationship's a linear relationship. We're not necessarily trying to make predictions. What we're trying to do is establish evidence of a theory that the dog's optimizing the path. So I'm going to do, I'm going to select calculate now. And notice the p-value here is quite small, meaning we have statistically significant evidence that the dog is optimizing the path, that the relationship's linear and the dog's optimizing the path. The other important statistic to look at is R squared. About 63% of the variation in y, the distance the dog chose not to run, is related to x, the distance the ball landed in perpendicular, out in the water, perpendicular to the shoreline. Okay, so, so here is the calculator output. So let's go through our interpretations here. So again, recapping, the statistical hypothesis, the null is that beta is equal to 0, and the alternate is that beta is greater than 0. The p-value ends up being approximately 0.000000007. This p-value is small. Who remembers what a small p-value means? Small p-values mean reject H0. So this is really cool. Okay, so this p-value is telling me that the data provides statistically significant evidence that the relationship between x and y is linear, and specifically it's positive. Now, what else can we take from this? Well, I think R squared is also something important to look at. Now, R squared is equal to approximately 0.63, or what we would say is about 63% of the variation in the distance Elvis chose not to run, because that was the y variable, down the beach, is attributable to the distance the ball landed. I'm oh, you doggone you thing. Oh man. Oh, that's awful. Can't believe that happened. My pen touched this little, you can't even see this, but I have this little thing in the corner it touched. But in any case, let me rewrite that. So R squared is about 0.63. And what that means is about, I'll just rewrite it. Let's see, about 63% of the variation in the distance I'm going to call Elvis the dog. I feel bad about that. So I'm just going to call the distance Elvis chose not to run down the beach is attributable or sometimes we say explained by or attributable to the distance the ball landed in the water directly out from shore. That makes sense. So the idea I'm trying to capture here is that the x distance, if you remember the diagram here, let me see if I can draw it here, just a little sketch. So the diagram basically that we're working from looks something like this. So so the distance here was the y distance, that was the y variable. And basically we're saying the distance the dog chose not to run is dependent on this x variable, which is the distance the ball landed directly out from the shoreline here. And so the calculus part that we worked on established the fact that if the dog's optimizing a path, then the relationship between x and y is a positive linear relationship. And the data is giving us statistically significant evidence that that's the case. And furthermore, about 63% of the variability in the distance that dog chose not to run can be attributed to how far the ball landed out in the water, which means the distance the dog chose not to run is directly related to or linearly related to how far the ball lands in the water. And again, that's another way to think about the idea that the dog's optimizing the path by minimizing the time. Now, there's one more piece of this puzzle that we need to look at, which is the residual analysis. And this is a really good example for residual analysis. And again, I've gone through this in previous lectures, so I'm not going to go through the calculator steps for drawing this residual plot again. But I do want to talk about the pattern, because this is an example of what the book refers to as a trumpet-shaped pattern in the residuals. And I think this is a really interesting and important part of the analysis. So the trumpet-shaped pattern that we're seeing in this particular residual plot, this trumpet-shaped pattern is implying the variation. Now remember, we're talking about y here. Y, these residuals are the differences between the observed and the predicted values. So this trumpet-shaped pattern implies that the variability in y is increasing as x increases. And generally speaking, this is a problem for regression analysis. And this trumpet-shaped pattern, if our interest were really in trying to predict how far the dog would choose not to run, which is something we could try to do with this model as well, then the trumpet-shaped pattern would be a problem, because it would be saying that predictions would be less reliable the further the ball landed out in the water. Now, I'm going to think about this in a slightly different way, because I think the trumpet-shaped residual pattern makes perfect sense, and it's very congruent with our theory that the dog is trying to optimize this path. And the reason is it has several different elements to it. First of all, Dogs have very poor eyesight. So when the ball's landing close into shore, or when X is down in this range, the dog's going to be doing better because of its eyesight than when the ball is landing further out in the lake, because the dog is probably not going to be able to see where that ball is or remind itself of where the ball is. It's going to have to do that from memory more so. And I think the dog would probably see the splash out in the water and then would mark that spot. And in fact, I used to do some training with field trial retrievers, and those dogs can mark multiple targets in the water and remember where they are. So there's no doubt in my mind the dog can see a splash and swim to that splash. But the thing is, the accuracy of the dog is going to probably diminish as X increases. Now, the second thing I think that might be in play here is that the ball is not static in the water. The ball is drifting. There's wind drift, there could be a current, there could be other factors that are causing the ball to move. So the dog sees the ball land in the water, marks that spot, and then optimizes the path to where the ball was. So the fact we're seeing an increase in variation and a decrease in the reliability of the model as X is increasing is really congruent with the physical situation I think that's happening with the dog and with Elvis and the theory that Elvis is optimizing the path for the dog. So the conclusion here I would make has several different elements. One element is p-value is very small. This is strong statistical evidence. The relationship between the variables is a positive linear relationship. R squared is relatively big. It's telling us that about 63% of the variation in the distance the dog chose not to run is attributable to how far the ball landed in the water. And again, that's quite a large amount of variation. That's a pretty large R squared value, really. And additionally, again, if you read through that entire article, what you'll see is that the sampling design Professor Penning uses is pretty low tech, and it's really subject to errors. In other words, in a nutshell, what Professor Penning's doing is throwing the ball for the dog and chasing behind the dog, putting a screwdriver in the sand at the point where the dog jumps into the water, and then takes the tape measure and swims out to the ball with the dog to measure the distance of the ball. So again, it makes a lot of sense to me that we're seeing this trumpet-shaped pattern also due to the sampling design, because the further that ball lands in the water, the greater the opportunities for those types of sampling errors. I think it's rather extraordinary that the results are so significant given the scenario, the drifting, the likelihood that ball's drifting, the fact that, just the fact that Professor Pennings is chasing his dog is going to, at times, mess with the dog's head a little bit. Because when the handler chases the dog, the dog has a tendency to look back, see what's going on. Hey, why are you chasing me? What's going on here? Sometimes the dog may even, decide to play with the person swimming to the ball, all that kind of stuff. So there's lots of errors possible. And again, that I think is what we're seeing in this residual plot. So I hope you enjoyed this example. I think it's a very interesting one. And